Hi everyone, and welcome to another video of this channel. So today we will be talking about a shape in multiple dimensions, and it is called an n-simplex. So this thing right here, it's a very simple shape actually, as the name implies. So an n-simplex, think about that as a triangle in n dimensions. So what do I mean by that? Well, a zero-dimensional simplex is a point, that's how we define it. And then a line segment with length 1 is a one-dimensional simplex, right? And this has length 1. That's what we call a one-simplex. Then a two-simplex is also an equilateral triangle with side length of 1. And then, of course, a tetrahedron, a regular tetrahedron with side length 1, right? This is the base in red, and it is a three-dimensional simplex. And once again, it also has side length 1. And so notice that this is called an n-simplex. What this means is that we can draw something like this for a very large simplex, so like an 100 simplex. So basically you can notice from this pattern right here that an n-simplex is a polytope, which is just a polygon generalized to any number of dimensions, and it's a polytope with n plus 1 vertices. So for instance, a line segment has 2 vertices because 1 plus 1 is 2. An equilateral triangle has 3 vertices, right? 2 plus 1 is 3, and so on. And so since n plus 1 is the smallest number of vertices that a two-dimensional polytope can have, this simplex right here is actually the simplest polytope that exists in a given dimension. Okay, so enough of an introduction. We now want to find how much n-dimensional space this simplex takes up. So we already have an equivalent for the amount of n-dimensional space that a triangle takes up and a tetrahedron takes up, right? We know that a two-simplex, it's just the triangle, equilateral triangle. The formula for that is area equals base over height. That's the equivalent of what we are trying to find, the n-dimensional volume of a simplex. And we know that it's a well-known formula is just a root 3 over 4. And then we can do the same thing for a tetrahedron. Remember our tetrahedron volume formulas, and we get 1 over 6 root 2. But what the question is asking fundamentally is how we can extend it to a 4 simplex or a 100 simplex. This is a very interesting question because in the end, actually, we will be able to find a very tangible mathematical result for something that we really can't visualize yet. So this is an interesting problem. It's interesting how this would turn out. And first, we will label some variables as usual. So we will let Vn be the n-dimensional volume of an n-simplex. And then, for instance, this right here, the 2-simplex volume is V2, and the 3-simplex volume is V3. So essentially, we want to find Vn, and we want to do this in terms of n. So now, what we can notice, we notice one very important observation. This single observation is very crucial to the entire video. And that is that the base of an n-simplex is an n-1 simplex. So what do I mean by that? Well, notice that each simplex right here in the diagram is composed of a base simplex. So in the case of an equilateral triangle, the base is a line segment with length 1. In the case of a tetrahedron, it's an equilateral triangle, right, with area V2. So this is what the base is composed of. This is what a simplex is composed of. It's composed of a base and another point. And we notice that this is true for any n-simplex in general. So basically, what we can say is we can express Vn in terms of Vn minus 1. So we express the volume of the entire simplex in terms of the volume of the base. Okay. So let's visualize this setup with finding the volume of a simplex by drawing a 3-simplex here. So everything that I write and draw for this 3-simplex also applies and generalizes without loss of generality to any higher dimensional simplex. Or any higher dimensional shape, actually, just for this segment of the video. Okay, so this big simplex has volume Vn, and the base has volume Vn minus 1. And then we also have this point right here, and the height of the simplex is Hn. So the height we can define as the distance between this point, this highest point that's not on the base, and the projection of this point onto the base. So that's like a more mathy definition of height, but this is essentially what the height is, and it also generalizes to higher dimensions. So now what we can do is, our plan is to actually evaluate this thing right here using an integral. So how do we do this? Well, first, we make a slice through the simplex at some point, right? And this slice is the equivalent of being parallel to the n minus one dimensional base. So the slice cuts an n minus one dimensional cross section through the simplex. And this thing right here, it is also perpendicular to the height, or normal to the height is the more correct way of putting it. And we can label this new height of this smaller resulting shape that we get with the green volume as our base as x. And then this green area is b of x. So b stands for base, and then I would say b of x because the volume of this base is a function of the height, so where we make the slice. And notice that if we assign, right, a tiny thickness to each of these green slices, we can express Vn in terms of an integral. So so basically, as these slices dx get really tiny, this b of x times dx turns into triangular prism. So we have this integral for the volume from x equals 0 to hn of b of x times dx, right? We're adding up infinitely many of them. And so now we want to express b of x in terms of Vn minus 1, so the base, and Hn, and maybe even x. So we can set up this little similarity relationship. So notice that these simplexes here, so one is an n-simplex, and then the other is a scaled version of that n-simplex. And then, so we can say that this is a similarity ratio, right? We can set up a similarity ratio. Those work in 3 dimensions and in 2 dimensions, so they also work in higher dimensions as well. And so we can say that the ratio of the bases is equal to the ratio of the heights, right? Hn over x. However, we also have to take into account that the bases are n minus 1 dimensional, and the heights are 1 dimensional. So we have to raise the heights here to the n minus first power. So with this very simple relationship, we can now say that b of x, right, after just simplifying, that is equal to this expression right here. And then, of course, we can plug this expression for b of x in terms of Vn minus 1, Hn, and x into the integral expression. So we have this thing right here is equal to Vn. Now, this Vn minus 1 over Hn to the n minus first power, that is all a constant. That does not depend on x. And then the rest we can just calculate using very basic integration techniques in a single variable. And this integral actually comes out to, when we evaluate at the bounds, it comes out to Vn minus 1 times Hn over n. And this formula actually is the reason why V2 equals V1, so the base, times the height over 2. That's why the over 2 comes up, because that's the dimension of the triangle. And same thing for the tetrahedron. The reason why the 3 comes out in cone formulas and in pyramid formulas is because that's the dimension of the space you're in. So that's just a coincidence. That's actually mathematically proven. We just proved it right here. And apparently this also extends into higher dimensions as well. But now we can go a step further than this formula, because this isn't in terms of n just yet. So we can say that since Vn minus 1 is also an n minus 1 simplex, right, this formula also applies to in that case. This formula applies to Vn minus 1. And so rewriting Vn as Hn over n times Vn minus 1, right, Vn minus 1 can also be written as Hn minus 1 over n minus 1 times Vn minus 2. And then we can keep going, we can simplify all of the V's until finally we have a product like this. So this right here, notice that Vn just depends on all these heights multiplied together and V0. So this right here, we can simplify like this. Notice that the product of all the terms from 1 to n is just n factorial. And then V0 is 1 because V0 is the amount of zero-dimensional space that a point takes up, right? Because at 0 dimensions, a point, and that of course takes up 1 unit of zero-dimensional space. So this is actually the volume, Vn, in terms of the heights multiplied together divided by n factorial. Okay, so we have gotten a step closer to finding this volume in terms of n. But now our goal is to find the height in terms of n. Because when we do that, we will actually have a formula for Vn. And so similarly, how I illustrated this case for when we calculated the integral on a pyramid or a tetrahedron, this thing right here, this next step of our problem solving will involve a lot more expressions that may be harder to visualize. So I'll actually go a dimension down for our visualization, and I will visualize all of these quantities that I will be talking about on a triangle, not a tetrahedron, a triangle. But similarly, it also applies to all higher dimensional shapes. We can do this without loss of generality. It still works the same for all simplexes. Okay, so notice that once again, this big simplex has volume Vn, the base has volume Vn minus 1, and the height is just Hn, and the side length is 1, right? That is just by the definition of a simplex, the side length is 1. Okay. And now let's take a couple more steps. So first, each simplex has a center of mass. This makes sense because all points are equidistant from the center of mass. Because all the edge lengths are 1, it really makes sense to have a center of mass here. And all simplexes have a center of mass. Right? Mathematically, if you want to find this analytically, the center of mass, you can take the average of all the coordinates. So we can label the center of mass O, and this is the centroid of the simplex, of the n-simplex. And then this point, right, this foot of the altitude, we can label it C. And just like the n-simplex and n-1 simplex, base, of course, also has a centroid, and this is the centroid of the n-1 simplex, of the n-1 simplex base. It's also the foot of the altitude to the base. And then this vertex from which we are drawing the altitude, we can label that as A. And in this case, A is the apex. So really nothing special. It's the only vertex that's not on the base. And then we can choose any of the remaining n vertices on the base, and we could call any one of them x, right? So this is just any base vertex. Okay. So now we introduce some more expressions into this. So it may seem unnecessary, but this is actually going to help us a lot. So this right here, we can draw a line OX, and we can call this Rn. So notice that by the definition of a circumradius, this is actually the circumradius of our simplex. So this is in effect the radius of the hypersphere, I guess that's how you would call it, of the simplex that we are talking about. And then the distance from C to X is also the circumradius, but this time it's of the n-1 simplex base. And so this is Rn-1. Okay. So these Rn and Rn-1 have specific values depending on the n, right? But they always exist. And so using these values right here, we can actually consider some of the triangles present in this diagram, and we can start setting up some equations. So first we consider triangle ACX. So triangle ACX is this big triangle. In the diagram, it splits the simplex in half. Doesn't always look like this, but yes. But once again, all of this generalizes to a higher dimensional case. So this triangle ACX, of course, it exists because AC and X exists in all simplexes. And notice that since HN is an altitude, ACX is a right triangle. And so because of that, we can apply the Pythagorean theorem. So here we have an equation relating the height and the circumradius of the base. But now there's another triangle in here, and the other triangle is OCX, and this one's also a right triangle. So this one right here, this little triangle. And two of the sides, of course, we know Rn and Rn minus 1 are pretty straightforward. This OC segment is Hn minus Rn. So we can square it, and we can add Rn minus 1 squared, and that will be equal to Rn squared, right? This is just the Pythagorean theorem. So now we have two equations, and we will see which ones we can manipulate. So we can expand the square out, right, to get this. We add Rn minus 1 squared, right? And that's equal to Rn squared. So this part right here, Hn squared minus 2Hn Rn plus Rn squared, that's the parentheses expression expanded. And we add Rn minus 1 squared, and that's equal to Rn squared. So now a whole ton of things go away. So the Rn squared cancels. And then notice that these two quantities right here, they're added up. And that is the same thing as adding these two quantities here. And as we know, that's equal to 1. And so we have that 1, which is the sum of the two blue quantities, is 2Hn Rn. And that's equal to 0 because the Rn squareds cancel. And so now we have an expression that relates Rn and Hn. So Rn equals 1 over 2Hn. Which is actually a pretty nice result. It's actually like a really nice thing that we just calculated. But now what we can do is, since this thing right here, this whole thing that we set up works just as well for an n-1 simplex as for an n-simplex, we can plug this expression into here. We can substitute n-1 for n, and we can plug it into here. So what we get is we are effectively substituting 1 over 2Hn minus 1 for Rn minus 1 in the top blue circled equation. So then when we expand the square, the 1 over 2 turns into 1 over 4, and then we add Hn minus 1 squared. And then this is equal to 1. So this is just rewriting the top blue expression with this thing substituted in. And so now we have this beautiful recursive formula that we can use for Hn. We have, if we know the height of the n-1 dimensional simplex, we can plug this in to get the height of the n-dimensional simplex. That's actually pretty cool. If you think about it, we can actually now relate some of the heights that we have in our quotient for the volume when they are multiplied together. But this is still not writing the height in terms of n. So you want a closed form or an explicit formula for Hn. So we have to somehow try to manipulate this equation to get Hn in terms of n. And the truth is that this equation is pretty hard. It's hard to try to plug in something that would go in for Hn minus 1 and then try to work with that. That will lead a big complicated fraction, and it's pretty hard to work with. So instead, we will use a much more straightforward strategy, and that is we will list some initial values of Hn, right? Because we know some of the properties of lower dimensional simplexes, like a 2 simplex, a 3 simplex, even a 1 simplex. We know the properties of those types of shapes, and then once we list out those values, we can keep listing values, right, for higher dimensional simplexes beyond 4 dimensions. And then once we have that going, we can guess what the pattern is, because there probably is some pattern. We hope there is a pattern, and we try to guess that that pattern exists. And then once we guess at a formula for Hn, we try to prove this formula using induction. Right? Okay. So with that strategy in mind, it's a pretty straightforward strategy, nothing fancy, but we have a very good approach for attacking this problem. So here I'm going to make a table with the n, with values for n, values for Hn squared, and values for Hn plus 1 squared, right? And once again, just rewriting, Hn plus 1 squared equals 1 minus 1 over 4 Hn squared, right? This is just the recursion formula rewritten in a different way. And then notice that we can write some values now. And once again, I'm dealing with squares of the height because they appear here. There's really no place where the height isn't squared in this formula. So I'm going to leave the nasty square roots for the end. Okay, so this thing right here, our strategy will be to, once we found this value, to plug it into this formula, and this formula will spit out the next value for the height, the value of the height for the higher dimensional simplex, like a machine basically. Okay, so we notice that when n equals 1, so for a one-dimensional simplex, the height is just 1, right? That's the distance between the two endpoints. That's just 1. So that's pretty simple. So now we plug it into this expression for hn plus 1 squared. So this thing right here would be h2, the height of the two-dimensional simplex. And 1 minus 1/4 is just 3/4. So after running this a couple of times, we get this nice list. So now we know the height for the first 8 simplexes. And still, these fractions seem to be jumping around. Like, they're all very familiar, but they're kind of jumping around. So what I'm going to do is I'm going to rewrite some of the values. So I'm going to rewrite all the odd number values with even numerators and denominators. So like this, and then 4/7 turns into 8/14, right? And I'm doing this because now the pattern is very easy to spot. So look at the numerators of each of these terms, right? We have 2, 3, 4, 5, 6, 7, 8, 9. So I'm pretty sure all of you can guess the pattern by now. The numerator is just one more than n. And then the denominator is 2, 4, 6, 8, 10, 12, 14, 16, right? Once again, very straightforward pattern. That's just 2 times the dimension. So what we're going to guess is that for an arbitrary n-simplex, the height squared is n plus 1 over 2n. This is a very straightforward pattern. So now we guess that hn is equal to the square root of n plus 1 over 2n. And now our job is to prove this using induction. So we have to prove that hn squared equals n plus 1 over 2n. So typically when we're doing an induction proof, we start with a base case, but once again, we already proved the base case. So now we go over to the induction hypothesis. And that is, so the inductive step, if we are given that for some value of hn, this formula works, then we want to see if this formula works for the next value, right? And we notice that if we use this recursion right here, this recursion right here, and we plug hn squared equals n plus 1 over 2n into this denominator, what we get is 4 times n plus 1 over 2n. And then this fraction simplifies a lot, and we do indeed come out that the height is n plus 2 over 2 times n plus 1. So once again, in this case, the numerator is n plus 2, the dimension is n plus 1, so that checks out, and the denominator is 2 times n plus 1. So that's a very straightforward proof. That is basically the end of our proof for using induction. That's pretty nice. So we now know that hn equals the square root of n plus 1 over 2n is indeed the pattern. So our strategy actually proved very effective for doing this. Okay. So this is the closed form for h of n that we were seeking. And now, once again, we're not done yet. We have to keep our eye on the problem. So the problem was find an expression for v of n in terms of n. So once again, we remember that we calculated v of n in terms of the product of all the heights. So we want a closed form for the height. Well, now, after this long journey, we have a closed form for the height. So I'm going to rewrite the height like this, basically not changing the value, just rewriting it as separate square roots. So now we can remember our formula that that Vn equals Hn times Hn minus 1 times Hn minus 2 and so on onto times H3 times H2 times H1 and all over n factorial. But now we can plug this formula into each height. So Hn, that's just equal to this right here. I'm going to zoom in a bit. Then Hn minus 1, if we plug n minus 1 for n in this formula, we get root n over root n minus 1. And then we can multiply, so on and so on. So now one really convenient thing about this is that a lot of this stuff cancels. So the 1 over root n cancels with the root n. here in the next term, here in the next factor, we will have our root n minus 1 in the numerator. Here we have it in the denominator. That cancels as well. And this is a telescoping product. So this thing will actually fold up like a telescope. All the messy square roots canceled, or almost all of them did. That took care of that, and all that's left is the root of n plus 1 and root 1, which is, of course, 1. And then here, notice that we have a lot of 1 over root 2's. So notice that we had n terms here from hn to h1. That was n terms. And all of these 1 over the square root of 2's are multiplied together n times. So that's just it. And so now the n, right, that's equal to the square root of n plus 1 in the numerator. Then these 1 over root 2's in the numerator translate to root 2's in the denominator of this big fraction. And we get root 2 to the power of n, because there's n of them, times n factorial. And that is finally it. So if you want to find the number, the amount of space that 100 simplex takes up, the amount of 100 dimensional space that 100 simplex takes up, you just plug it into this formula, and that will give you the answer. That's actually pretty cool. Like, I was pretty amazed with this fact when I first saw it, that you can actually find a volume of something so weird, and have a very concrete formula in terms of the dimension using this thing right here. Okay, so notice that as a quick sanity check, right? V2. Let's just try this out on a couple of values that we are familiar with. So V2, using this formula, if we just run it through, right, like this, root 3 is root 3, then root 2 squared is 2, 2 factorial is 2, we get root 3 over 4. And that does match up with what we would expect it to. And then for 3 dimensions, it also works. Yep, it works because it's 1 over 6 root 2. So that's actually pretty nice, that this actually works for higher dimensions. And for V4, that would be root 5 over 4 times 24. So that's root 5 over 96. That's already, yeah, so that's an expression for the amount of n-dimensional, 4-dimensional space that a 4 simplex takes up. And it's pretty nice that we can actually have this type of formula. So an interesting result is actually what some of these values converge to. So we notice that Vn, right, it converges to 0 as n approaches infinity. And that is because if you try evaluating this limit, you can use L'Hopital's rule is actually kind of hard here because you have an n factorial in the denominator, but it's pretty obvious that the square root of n plus 1 grows much slower than this function by itself, let alone multiplied by this huge function by itself, right? If you plug in 100 for this value, you would get something slightly over 10. For this value, you would get 2 to the 50th, which is a huge number, and for this one, you would get 100 to 100 factorial, which is an even bigger number. So basically, this approaches 0 very, very, very quickly. That's actually kind of interesting that the simplest shape in an infinite dimensional space, if you think about it, like if you want to take it to the limit, actually occupies 0 units of space. And then the height, on the other hand, actually approaches a non-zero value, because the height is the square root of n plus 1 all over 2n, right? If we go up here to what the height was. And then this, of course, n plus 1 and n in the square root, they grow in the same way. So all that's left when you take the limit as n approaches infinity is 1 over the square root of 2, which is also pretty nice. So the volume shrinks to 0, but the height actually stays virtually constant here. So that's also a very interesting result, how the simplex behaves. And you can actually try this exercise out for other values, such as Rn that we investigated. How does the radius behave? And so on and so on. Okay. So I hope you enjoyed this foray into higher dimensions, and I will see you in my next video.